It's fine.
Okay, let's go ahead and get started today. We'll probably have a few more folks join in. And start as usual with announcements, and then we'll do review. So as you're sitting here, if you got any questions, do like Trinity, put them in the chat over there, and we'll start working any of those from anything from book 1. Great, Lauren. And then we'll go over the new material, which is starting book 1.5. Okay, so the first main announcement is that our next live class, because next week is the Thanksgiving break, we're going to have our next live class on Monday. So please, if one of your teammates isn't here, shoot them an email, shoot them a text, just to remind them that our next live class is Monday, November 23rd. So there will be, we're switching from that Wednesday, which is the Wednesday before Thanksgiving, pushing it forward to Monday, because I want to make sure we have time to do these live review questions. Okay, next, a couple announcements through Oaks. So I'm going to share the screen. Thanks, Will. Guys, keep putting questions over there in the chat. We'll get to those. For now, I want to just talk about a few other announcements within Oaks. So I'm going to share my screen. And we're going to go to the content. This is what it looks like on my end, the instructor side of Oaks for your section. Okay, so assignments from, this is one thing I wanted to note. I'm sure you guys will see this, that this, at the end of module 4, which you're currently working on, you have some assignments due tonight at 11:59, and we'll be able to practice any problems related to those today in class. But also notice this optional review. These are from the entire Journal 1, old exams. Were we to be in the traditional in-class semester, these is what you would have instead of these challenge problems. So those challenge problems are taking the place of these exams. These are the concepts you're supposed to know. So this is good. It was optional. You don't have to submit anything. I just wanted you to take a look at it, print it out, have it ready when it's time to start studying for the final exam, which is a good time to start slowly working your way through these. And so you can see the types of problems that you will see on the final exam. You'll have the usual things that you see in your quizzes, some concept questions which appear at the end of your chapter reviews. You'll have some calculation questions. So these are some of the typical concept questions. And then the second part of this particular exam, you see some calculation questions, which again are similar to what you see on your quizzes, similar to what you see on your end of chapter reviews. And so these are ones that I've taken. It shows you the level of difficulty and what we're expecting. And you want to make sure that you can work through these. You should be familiar. Bring questions. If you take a look and want to bring questions for these for next week, that'd be a good idea. Bring questions to the math lab, to Chloe. And as usual, I think I mentioned this last time, I get lots of analytics about this class. So from the math lab, I get who's attending. And so all that's helpful for me if I'm going to bump your grade up, if you're at the borderline of a plus minus grade. So who's using the math lab, how often, who you're seeing. I get Oaks analytics for how often you're going through your assignments, if you're replying to any discussion boards we've had, how many videos, how long you're watching them. So it gives a ton of information. And then also YouTube gives me that as well, and the Google Docs. So the Google Docs is helpful for your challenge problems, and that's how Chloe was able to do the grading. You should have got an email about that with your challenge problems. And so that's the next thing I want to share, to talk about what is good work and expected work. And so there are a couple really good groups I want to do shout outs for. So let's see. I think this is my 221 class, so I need to go back to you guys. Okay, so then there was group 1, which is Alyssa, Reagan, Wade, and Alex. Really nice job on this challenge, so I want to take a look at that. Okay, so here. So again, they chose their color font. They each wrote and back and forth to each other. And again, I can see the trail of this and the timestamps on everything. I kind of go in and see all sorts of information about how well groups are working together. But you can see like Miles chose this sort of purple color font, Reagan this pink one. And so they're writing comments back and forth to each other. Then clearly what each person thought their contribution was. Then they each wrote some information, a paragraph about this. This was the samples and examples that you saw from the 221 class, gave a nice example, and this group followed that carefully. And then there were some other groups that Chloe really had a hard time deciding if a particular teammate did anything. And if you want to challenge that, you can definitely, she should have put that in the email, like, hey, I helped, I just forgot to write. Well, then you're gonna have to demonstrate that to us sort of orally that you understand that problem. Okay, so then let's get to their final report here. Again, they followed the instructions and wrote the methods section, what they were trying to do, showed a little screenshot that they pulled out from a tech tool. They put the 3 points on there where the statue was, very clear to visualize, everything was laid out. Then they start working through the function, taking the derivative of each part of it, showing the derivative that they got, plugging that into different points to get the tangent lines. They found the equation of the different tangent lines, beautifully entered here in Desmos. Each line has a different color, which one was closest to the statue, this green one. So vehicle 2. And then they went through the conclusion. Again, it was this, how confident are they in that answer, that it might hold up in a court of law. And then I want to point out, so excellent work again, Alyssa, Reagan, Wade, and Alex, just to see a model of what really works. Next group is group 2. This was Ilaria, Lauren E., Elise. It wasn't clear though, John's contribution here. I think he was part of that group, but it wasn't clear what his contribution was. So John's got his name, but then we didn't see much green anywhere else. Looks like the three ladies worked on this. Some images and tools as they're working, and then they get together, each of them write their contribution. And then their final report, again, similar, but very clear again what each, I love the use of sort of graphic design and layout on this. Boldface, really easy for Chloe and I to grade this and take a look, okay, yeah, that's the equation right here in boldface for vehicle 1. This was also really nice because they showed their by hand work. So sometimes that's a lot easier and more efficient. You can mix this blend of the tech tool plus by hand work. Yeah, and then similar graph with Desmos. Oh, this was cool too. They zoomed in. Yeah, and got many different ways of looking at the problem, but I have no doubt that the 3 folks that really worked hard on that, Ilaria, Lauren, and Elise, understand how to get the equation of a tangent line at a particular point, which is fundamental idea you need for this class. Okay, next one, group 3. This was Merritt, Emily M. And another really nice job following instructions, clear who is doing which parts of the project and their teamwork. Laid out nicely again with these sections in their report. This is all that Chloe and I have to grade you. This is, again, taking the weight of an exam. So I think a lot of groups just didn't take that part seriously and sort of handed in subpar work. And this is the point that Chloe and I wanted to make sure every group, oh, this was cool. Yeah, they showed the points clearly with the labels, derivatives, again, handwritten work. And then another nice graph, just like group one, with all three of them laid out and their conclusion. Okay, one last one that I really liked, and then we'll talk about the groups that weren't maybe as happy with their grades and what you can do about that. So group 19, this was Lauren A., Aiden, Olive, and John. Okay, again, each group member detailing their contributions, their final report. Oh yeah, this one was cool because they chose the murder mystery. This is one of the few groups that chose this problem. Figuring out the temperature. Got their, the key piece of this one was figuring out the K value, the cooling rate, and that wasn't exactly straightforward. So it took a little ingenuity to figure that out. And then once you had that, plugging that in and figuring out that the murder had occurred around 3:21, and they were added some precision to the seconds. So it was 32 seconds, had to be Mrs. Peabody. Cool. Okay, so again, those are some excellent examples of teams that worked well together and what is expected of these challenge problems. You've got 2 more this semester before a final exam, and you really want to put your effort into those. There were a couple groups that seemed quite dysfunctional, I might say. So if that's you, if you got some, like, what can I say, dirt, like duds in your group or turds, like, you have to figure out how you're going to do that. It might be that just a couple of you say, well, the 2 of us are replying to text and understanding this. Let's go ahead and work on our own. That's totally fine. And those other folks have to figure out their own way then. And so if you want to do that, make a little subgroup. But the point is, and I think I've gotten a few emails from folks that are like, I really want to learn this, but I'm having a hard time with my group. Well, it might be, again, that you might have to be a lone ranger or go off with one other member of the group, but you have access to Chloe and I. And in particular, Chloe is in the math lab 4 or 5 days a week for like large blocks of time, that it would be free access to her. She understands the problems. And so in general, though, our philosophy is that you can resubmit something. So for any of our education majors, there's 2 types of evaluations. There's formative evaluation and summative. And summative's like, you got one shot at it and that's it. Formative is, we want you to continue forming ideas and developing and understanding this material. So if this last challenge problem, you and your group just didn't give it your all and didn't, jump over that bar that you said, you really just sort of half-assed it. If you can admit that and you're ready to submit something and truly understand it, and you possibly need help, reach out to Chloe and I for help to do that. But I also understand that you probably, if you looked at it again and really gave it your all, you could do those challenge problems. And so you can resubmit. You won't get full credit, but sometimes you might have had a 50. I mean, there are some groups that really hardly did anything. In fact, Chloe was being a bit generous to give a 50. Sometimes I thought that one really deserved a 20. Well, if you're the group with the 50 and you want to do something about that, you can. Again, you won't get 100, but the sooner you resubmit, the longer you wait, I guess that sort of decays the chance to get a higher grade. But resubmit, and if it's good work, again, you're going to get much improved over that 50. Okay. All right, so questions for me about that at this point. So any logistics questions about running the class, and then we'll go to the review questions from last week. Okay, so I see a couple questions about logistics, so we'll take those and then we'll go to the specific sort of calculation questions. So first question, DeMarco. So yeah, if you can go through the ones on that optional, I don't know what I call it, optional review from Journal 1. You finish Journal 1, which the keyword for that is derivatives. If you can go through those problems on exam 1 and exam 2, that's a good you're well set for Journal 1. And then we haven't done Journal 1.5. We're about to get started with that, but it'll be similar flavor, similar level of difficulty. Those exams have both concept and calculation. Again, your final exam will have concept and calculation questions. The final exam will be during the final exam period, which, who helped us with that last week? That was like, what, December, what did we say? It's a Saturday, December 12th, 3:30 to 5:30. So it's just a 2-hour time slot, and it will be on Oaks, proctored. And so I'm waiting for the math department to give me some instructions about what that proctoring means. It might be that you all have to be somewhere where you're on Zoom and I'm watching. You have to be able that I can see the screen. Some of you are turned off your video, but you have to open your video, and you will be taking your exam on your laptop on Oaks, proctored through Zoom, and possibly with something called Respondus, which you might have been using with your other classes, and that's some sort of browser lockdown. So I'll have more details as we get closer, as that information is coming to me. But in general, the format of the final will be very similar to your quizzes in Oaks, but like extended format. So your quizzes in Oaks might be anywhere from 5 to 10 questions. Your final exam, we're probably looking at 25 to 35 questions, concept questions, just like you have on your quizzes, and then some calculation questions, which are similar to that practice that DeMarco was asking about. Okay, so other questions for me on the logistics of the class? And for anybody that came in late, the key thing was our next live class is Monday, November 23rd, rather than next Wednesday. So we're pushing it forward a couple days so we can make sure we have a live class together. Okay, so then if you have more logistics questions, put them in the chat, or more calculation questions, put them over there in the chat. And for now, we'll just start taking these one by one. So it looks like there's a couple questions from page 294 and then a couple from 315. So let's start on page 294 in Journal 1. And quite a few on this page. Okay, we'll start with number 2, Will's question. Find the local extrema for this function. F of x is x to the 6th minus 6x to the 5th. Okay, so local extrema, just to review too for the final exam, you have 2 ways to do this. So just take a moment and make sure you got those in your head. What are the 2 ways to find local extrema? First derivative test, second derivative test. Okay, and so for the first derivative test, I think that's what it specifically says here, but on the final exam, you have your choice. So let's do this problem with the first derivative test, and then we'll just talk about how we might do it with the second derivative test. So the first derivative test, just to have in your head the little picture that goes with this, study guide. For the final exam, the first derivative test, you draw your f prime line, you put your CPs, suppose there were 2, you pick a point from each interval, you plug it into the derivative, that's why you've labeled it. And then when you have a sign change, you have an extrema. And depending on the type of sign change, this plus sign means it's increasing. So we're going increasing to decreasing. So that CP is actually a local max. And vice versa, this would be a local min, because we change from decreasing, pedaling downhill to uphill, therefore we are a local min. So that's how you interpret a sign chart. Let's actually make the sign chart for this one. So I assume Will's question, there might be some piece of this where it's a little bit tough with the pre-calculus, which is the factoring. Because probably at this point, no problem on this derivative. This is a nice polynomial one. Okay, I take the derivative and I set it to 0 because that's the definition of a CP. CPs are good places to look for extrema because they're places where you have a horizontal tangent line. Horizontal tangent lines sometimes happen when you have a max, and sometimes when you have a min, and sometimes when you have neither, you're actually snaking through like this, which was an inflection point. We have to determine which of those it is, and we will do that by doing this f prime line applied to our particular problem. Okay, so I set it to 0, and now I have this polynomial equation that I have to solve for x. The definition of solving an equation is a value of x that's going to make this a true statement. And maybe right away you can see something. Like if you plug in 0 for x, that's going to make 0 minus 0 is 0. So that would be a true statement. So we know one of our CPs that goes over here is 0, but there could be some other ones. So let's see what happens when we factor it. Rather than just guessing and checking, it's going to make more sense to do this in a systematic way. And so I'm going to take, let's see, there's a 6 in each thing, and there's an x to the 4th in each part. And then I'll be left with an x minus 5. Now I have two factors equal to 0. The only way two things can multiply together and be 0 is if at least one of those is 0. And so I can set each factor to 0. 6x to the 4th equals 0, and x minus 5 equals 0. This solves x equals 0. The only solution here is x is 0, so that's a CP. And then this one is a nice linear one. X is 5 is another CP. So it turns out there were just two CPs. You put them in order on a number line. And then we do as we say, we plug into the first derivative, pick a point in the 3. There's now 3 intervals. I pick a point from each one. So I try minus 1, like f prime of minus 1, f prime of 1, f prime of, say, 10. Just picking numbers that'll make it easy to do the arithmetic, but always plugging into the derivative, not the original function. The derivative tells you about slopes, which are going to tell us about increasing or decreasing. Okay, so I plug -1 into the first derivative. You can plug it in here or here. They are the same thing, right? So f prime of x, so I might be trying to find f prime of -1. That's -1 to the 4th is a positive, times -1 minus 5 is a negative. So a positive times a negative is a negative. This negative sign means it is decreasing on the interval from -infinity up to 0. And then I'm going to try +1. So when I plug a +1 in, I still get a positive in the first one. The second one would be a negative, so I'm still negative. I'm still decreasing. Lastly, I'm going to try 10. When I plug 10 into the derivative, I get a big positive number, but it's still positive. 10 minus 5 is positive, so positive times positive is positive. That positive sign means we are increasing from 5 to infinity. The CP at 0, it isn't a max or min. We thought there's a chance it could be, but it's not. It might be an inflection point, but we'd have to get the second derivative to answer that. For now, we can say, though, that this x equals 5 is a local min. Okay, questions on number 2.
Do you mind drawing out the actual graph? Like, what would it look like?
Yeah, that's a great question. Who asked that?
Lauren.
Lauren, thank you, Lauren. And I should always do that, right? It always helps us visualize. So let's just do a screen share. And let's go to Desmos. The original function, y equals x to the 6 minus, so I'm stuck in the exponent right now. I'm going to push the down arrow, brings me to minus 6x caret 5. And okay, so we are decreasing. This first one said you're decreasing from -infinity to 0. That's true. We'd be going, whoa, that's pretty steep downhill to ride my bike, but there we go. Levels out. It turns out this is a CP. It has a horizontal tangent line at 0, but that's not a max or a min because it just decreases some more. But that is actually an inflection point using our vocabulary, right? Because we're part of a smile from negative infinity to 0, and then part of a frown. So we're concave up, switch to concave down. Anytime you switch concavity, you are an inflection point. So that x equals 0, visually, from Lauren's question, we see it's actually an IP, an inflection point. To prove that, we'd have to go through and do the F double prime line, but that's not what the question asked, so I'm just overachieving there. So we are concave down, and then the next point we're saying here is a CP at 5, and let me just maybe zoom out first, might help. Yeah, because that's way down there. Whoa. I guess it makes sense because it'd be like 5 to the 4th. That's super big. Whoa. I didn't know this is gonna help us. That right there is at 5, and it went from down to up. Still looking like just a total crazy point. If you're on another one that maybe scale better, we'll try this in Google, because I think that auto scales a different way. Yeah, okay, so notice the y-axis is scaled by like thousands, and then the x-axis is only scaled by ones, just to make a prettier picture, which maybe some TIs automatically do, TI calculators. But at any rate, so what's actually happening on the Desmos scale, when you scale it to this scale that Google's using, you do see that that is a local min. And it also does change from decreasing to increasing, which is the definition of a local min. We are right there at 5, a horizontal tangent line. And what else can we say? We went from, we are concave up there as well. So we're concave down to maybe close to 4-ish. And then we switch to concave up. And we know by the second derivative test, that's also a way to check that x equals 5 is a local min. It's a CP, and if that CP's second derivative evaluates to a positive number, you're concave up. So we see all those things visually. Lauren, that's a great question. You're always like a teaching assistant by the questions you ask, like perfect timing. Okay, other questions on number 2? Okay, thank you, Shelby. Great question. So Shelby wants to know, for these kind of local min problems, how do you know when you're supposed to plug in X and solve for Y? And I think what she's asking, what Shelby's asking is, sometimes we give this as a point. So like when X is 5, we can write it in this sort of notation, which one of the groups did that. We saw that earlier on the challenge problem. Was it group 19 maybe? Did a really nice job showing those points on the function in point notation. So we know when X is 5, how do you get Y? Well, you always go back to the original function. So instead of getting derivatives, we want to plug in F of 5. So that's 5 to the 6th power minus 6 times 5 to the 5th power. Oh gosh, I don't even know. What is that? 5 to the 5th power times 5 minus 6. So that's a negative 5 to the 5th power. 25 times 25 times 5. 25 times 125. Negative of that. Oh, that's why it was so big in Desmos. 25 times 125. So some giant number. Let me get that real quick. 3,125. So negative 3,125. So if we wanted to write, didn't ask us to, but if we wanted to write this as a point, like the local min was way down there in that bottom value in Desmos, so we kept having to zoom out so we could see how far it was. Some problems will be very specific. So I guess the summary to Shelby's question is, some problems will be very specific and they'll say, give your answer as both X and Y coordinates. Some application problems, it's important to do that. Like I think it helped for that challenge number 1 that most of the groups did, to know exactly on the curve where you were getting the tangent and then how close you got to the statue. All right, so then there were a couple more on that page about local extrema, and these are good ones to go over. We'll take the time. I think we'll still have plenty of time to cover book 1.5, chapter 1. It's important to take this time because I can promise you, you will have a problem on the final exam. Find the local extrema for this function. You'll have a problem on the final exam. Find the global extrema for this function on this region. You will have a problem finding where this function is increasing and decreasing. You'll have a problem, where is this function concave, up and concave. All the ones that you saw on that optional review, those old exams from previous classes. Okay, so the next one on this page, number 6. Actually, I'm going to try Cheyenne's. Cheyenne's is number 7. They're kind of similar, so I think we just did one of Will's. So since we also want to get to Trinity's question, so let's do number 7. ln x squared plus 2x plus 4. Find the local extrema for this function. Well, first off, it's a little bit more complicated than the one we just did because the function is not just a basic polynomial. It's a polynomial, but it's trapped inside an ln right now. And so we need to first do the ln rule when we take the derivative. The ln rule is it's the derivative of the stuff over the stuff being what's in the parentheses. That's just the rule for the ln. That's how you take the derivative of a function that involves an ln. And so we'll have x squared plus 2x plus 4 in the denominator. We look at that and take its derivative, and now that's the easy part, right? 2x plus 2. And you're done. If the question, and there will be some ones like this on the final, they're just here's a function, take a derivative, but you'd be done if that was all it asked. It might say here's a function, find the CPs. Okay, no problem. We go to the next step. We set that function to 0. Even though it looks kind of complicated because we have this fraction equal to 0, you never want the denominator of a fraction to be 0 because that's undefined. And so we talked about this on the orientation, the pretest orientation module, was the only time a fraction can be 0 is if the numerator is 0. And so now that's a really nice, easy linear equation to solve. X is -1 because you're trying to solve 2x plus 2 equals 0 for x, 2x equals -2, x equals -1. Right, so that is your CP. So our F prime line for this particular problem is even easier because there's only one CP. So I only have to put one point on here. That divides it into 2 intervals. I pick a point from each interval and plug it into the derivative. So I might try something like F prime of negative, I don't know, 5, let's say, doesn't matter. F prime of +5. I'm really just checking the signs here. So I plug -5 into the derivative. Let's see, put that here. This is our derivative. So I want F prime of -5. That's going to be a negative in the numerator. and 25 minus 10, so the positive in the denominator. Negative divided by a positive is a negative, so we are decreasing. And then f prime of positive 5 will be a positive and a positive. Positive divided by positive is positive. And so we know the function goes decreasing to increasing. Okay, but that would be, we'd stop there if the question was find intervals of increase and decrease for this problem. We have all the information sitting here in the f prime. We'd say it is decreasing from minus infinity to minus 5. It is increasing from 5 to infinity. But it didn't ask that, it said find the local extrema. Because we have a sign change in our f prime, it means we go from decreasing to increasing. So this must be a local min. And if you wanted to write it the way Shelby asked about, we would say you could find the local min at the point -1, and then you need to go get the corresponding y value. And that's always back to the original function. So we plug in -1 for for x. So f of -1 would be ln of 1 minus 2 plus 4, which is what? Ln of 5, ln of 3. So whatever that decimal is, maybe it's like 1.7 maybe? I don't know. Ln of 3 goes there. Okay. Perfect. Thank you guys. So I'm seeing Aiden's question. Yeah, this is totally fine to ask questions about challenge problems during class. It might be that I push it towards the very end of the class at like right before we end. And so if you still have questions, but thank you, Trinity, for replying. That's a great answer. Yeah, so the neat thing about challenge 8 is you can be creative. I'm interested in your ideas. There isn't like, oh, I just need to do this particular calculation. Like maybe that was clear from challenge number 1 that you needed the calculation skills you needed were to know how to get the equation of a tangent line at different points on a function. And once you did that, sort of unlocked it. That was the calculation piece you needed. For challenge number 8, again, I'm not saying that it fits one of those, but you might think about how you could use ideas from anything in this book that we've covered, even things we haven't covered, but just ideas that you skimmed through or saw that might help you answer that. And you want to quantify it. I want you to think mathematically and use your creativity to answer this. It's not like there's going to be answer like 7 or Car 2 did it, right? Or Mrs. Peabody. This is for you guys to have fun and be creative, which you don't get often to do in math. And so this is kind of fun. If you want something that's more straightforward, challenge number 7, that's one where there's a piece of calculation that's required for that, and there is an answer. Put it at this point there's a beltway, and there's 2 suburbs, right? Isn't that one something like this? A beltway around a city, and there's like a point and a point, and we want to know where should we place it, an exit on this so that it's equidistant from those, or so that nobody, if I put the exit right here, like this suburb wins, but that one loses, right? So you want to make it so it's closer. And so you can sort of estimate, obviously, and visualize that, and that's a good thing to do with that Desmos, just kind of trying some different points. And then you know the distance formula between 2 points from Pythagorean theorem. But the calculation part of that is you want the point, where do I put this so that I minimize the sum of these distances? And you can write that out and then use a tech tool to help you do it. So it's a modeling question, and then you'll use a tech tool to help you with the calculation, because the calculation is actually beyond business calculus. Probably more like calculus 2 to do that. Okay. All right, so let's go back to, there's a couple more here in the chat that I want to go through. Let's go to Trinity's question next. So this is page 315. Oh, this is great. So You guys already had us practice local extrema. Again, that's sort of a highlight of calculus. And now Trinity's next question is, let's do global now. So this is really important. These are the highlights, and we want to make sure we got those down. So page 315, and I think, what did you say? Number 2. Okay, so this question, let's go through, we'll talk about the parts that are sort of review and then the parts that are take a little bit more effort. And general thing, this is a global extrema, so we don't use the F prime line. What's your sort of study guide image that helps you do global extrema? Global extrema only happen 2 places, CPs and EPs. So endpoints are always given. So we would put those in, x equals -2, x equals 3. We make a list. What else do we add to the list? We add any CPs that lie between those endpoints. If I get a CP of like 10, that's outside the endpoints, and I don't care. We have blinders on only on a certain section of this graph that we are interested in. And that section of the graph is from -2 to 3. Oh, and then this was something Lauren had asked earlier, so maybe this will be a good thing just to show y'all again. I think we did this last week, but never hurts to do it a couple times. So we went to Desmos. Let's put in our function, x divided by, whoops, get that first one out of there. X divided by 1 plus x squared. Yeah, oh yeah. Okay, so we went back to origin being the center of this, and we have this little snaking through the origin, but sort of asymptotes here gets closer and closer to the negative x-axis, then over here closer and closer to the positive x-axis. And we want global extrema. Now on the entire graph, that answer might be different, but we only want to look at the section that goes from -2 to +3. So you can do that by using a bracket, curly bracket there, and you say -2 less than or equal to, and then go up to +3, and then it hones in on just this section of the graph. So that is the part, again, we're focusing on. We just erased everything else, and that's the part we want to find our global max and global min. We see there is one global max here, and it even does a nice job on Desmos telling us that's when x equals +1, y equals 0.5, or f of x equals f of 1 equals 0.5. And then down here is our global min at x equals -1, f of -1, or y is equal to -0.5. It's possible that you could have ties for global max and global min, right? You could have more than one. That was by the extreme value theorem. The extreme value theorem said if your function is continuous, which ours was, right? There was no holes, jumps, or breaks on that section of the graph. If it's continuous on a closed interval, which they did, includes its endpoints, then your function is guaranteed to attain at least one global max and at least one global min. So at least tells you that there could be more than one. There could be 2 or 3 or infinitely many, even if you're talking about trig functions like a sine. But again, we don't do trig functions, and this does satisfy the EVT. It has to be that they gave you, when they ask about global extrema, they have to give you an interval of interest. This interval of interest gives us 2 endpoints. Those 2 endpoints then define a range for which, if there are any CPs, they have to lie in between those. So let's go now and figure out the CPs. And this is probably what, I think this was Trinity originally started this question. Trinity was probably wondering about this derivative. She probably had no problem with this part, and then was like, okay, how are we going to compute this derivative? Well, I think we did one like this last week too. I think Trinity asked it too, actually. we didn't have a differentiation rule where you wrote those on the side. We have this like little toolbox that we carry around with us of all our differentiation rules. What do you have at this point? Maybe eight different rules. Well, we don't have a rule that looks like a fraction. Like, what do we do when we have a fraction? We don't have a rule that fits it. So it has to be that I can somehow massage this to fit one of the rules I have. And I can kind of make this look like a product rule, right? I can say this is x times 1 plus x squared to the minus 1 power. Once I've written it like that, it looks like there are really two functions being multiplied together. And that's still f. I haven't taken a derivative. The first function, and this whole part here is a second function. And now we're going to have to do the product rule, first times derivative of the second plus the second times derivative of the first to this thing. And sometimes somewhere in there, we're going to need that other rule we did last week called the general power rule. Okay, so I'll write that in a moment. We'll come back for that. For now, let's just set up the structure of the derivative. F prime of x is the first times the derivative of the second plus the second times the derivative of the first. Okay, so we fill in our copying boxes. X goes here. 1 plus x squared all raised to the minus 1 power goes there. The last empty box is the derivative of x, which is just 1. And then what goes in this blank box, the derivative of our second function. And our second function, again, is going to be a general power rule. It is something in parentheses raised to a power, a negative 1 power. But it's more than just x to the negative 1, right? It's more than just a basic variable raised to a power. It's actually an expression, 1 plus x squared raised to a power. Oh, sorry, Macy. And so we need to then use the general power rule, which looks like this. If your function is some stuff beyond just x, we'll call it f of x. It has some x stuff raised to a power, then the derivative y prime or dy dx or f prime of x is times the power, so the n, take the function in parentheses down a power to n minus 1. So that's the part where it looks just like starts to look just like the power rule, times the derivative of what's inside, f prime of x. So times the power, down a power, times the derivative of what's inside. That's the general power rule. Again, it's just an extension of the basic power rule for something that involves more than just an x, right? It's 1 plus x squared. So that's what's going to go here. I'm going to use the general power rule. So times the power will be minus 1. Take the thing in parentheses, down a power, so I subtract 1, so that'll be minus 2, times the derivative of what's inside the parentheses, which is just 2x. Okay, that's just taking a derivative. So we spent quite a bit of time using this new general power rule. We only did it once last week. So next time doing it, this was a great question, Trinity. Thank you. All right, now we need to take this thing and set it to 0 because we want to get CPs. We want to know if there's anything that belongs there. All right, so this is going to be some more algebra that we're going to have to do. But before we do that, maybe we should think like Lauren's question always, which is what does this thing look like? Maybe we could guess at the CPs, and that might help us with as we go through our algebra. And I encourage you to plot things and sort of you still have to justify with the calculus, but I encourage you to use your tech tools, use your calculator to visualize what this looks like, and that'll help you verify the calculus. Okay, so to visualize what the CPs or take a guess at what the CPs might be, I would graph this function, if you're already done, over that region. So write minus 2 to 3. And we want to look at for CPs. Where are the places where you have horizontal tangent lines? Okay, so if I was, again, zooming in, I see right here at x equals 1 is a horizontal tangent line. So I'm thinking what's going to go on my list here is that there's a CP at x equals positive 1. And then if I go back here as well, I zoom in. Again, I'm traveling along, keep zooming in, and I see over here, I stop, and right there is a horizontal tangent line. If I were riding a roller coaster, I'd sail off horizontally. If I were riding it backwards, I'd also sail off horizontally. So you should be good at visually estimating CPs, places where you have a horizontal tangent line. This next one occurs at x equals -1. So I think my list should look like this. And let's see if that's the case. So I think this is what's going to happen when we do some algebra, but we're going to have to show that algebra. But let's just step back for a moment and get a big picture and talk about what are we trying to achieve here. Does it make sense? Am I okay to put the CP of -1 in here? Yeah, because CP of -1 lies between -2 and 3. Okay, that makes sense. The CP at +1 lies between -2 and 3. And then all I have to do, the last piece of the puzzle, is just to take those values and plug them into the original function f, because that gives you heights on the graph, right? Derivatives tell you steepnesses, how steep you are. F of x tells you how tall you are. F double prime, the second derivative, tells you how like curvy you are, right? Curvatures. Okay, so I'm going to take these 4 values. Those are the only, out of the infinitely many points between that little red section of the graph on Desmos, there's infinitely many points you could stop, but the cool part is calculus tells us there's only 4 that we have to check. Those 4, I figure out who's tallest and smallest by plugging into the original function. So let's go ahead and finish this, and then we'll come back and do Trinity's part with the algebra here. Let's go ahead and finish. Assume that our visualization was correct. These are the 4 points that I checked. When at the EP of -2, I'm just going to plug in -2 here. Let me make a little space right here to do this plugging in. F of -2. -2 divided by 1 plus 4 is 5, so -2/5, or -0.4. Then I'm going to try -1 and see what happens. I'll have -1 over +2. So that's -1/2, which is -0.5. Whoops. Then I need to try the third point, which is the CP at +1. When I plug in +1 to the function, I get 1/2, which is +1/2, which is +0.5. One more thing to plug in. The last of the 4 points is the EP at x equals +3. And that will give me 3 divided by 10, which is 0.3. So maybe it's easier turning them into decimals to decide who is the tallest and who is the smallest. So the largest y value on the graph is right here. And then we can say this CP is more than just a CP. It's true, it's a CP, but it can get an upgrade. It is a global max on that interval. It turns out that it's actually the global max on the entire function, because if you remember those asymptotes, right, it would just keep on going. So, but it only asks us on this interval. So this is also the correct statement. Okay, and then the global min. Who is the smallest out of these 4 values? The smallest one is -0.5. That is your global min. Okay, we were able to do all of that, understanding our vocabulary, visualizing things with a tech tool, and we did part of the stuff taking this derivative. The only thing we haven't done is verifying, showing our work, because you have to submit your work on the final exam. There's actually an assessment team that goes through all of this in grades, shows the work, particularly during this COVID semester. So we have to show our work. So let's make sure we finish this. We know what the answer is, and this will help us check. We need to find these CPs. We have this big long equation equal to 0. That's intimidating. It looks kind of crazy, but let's use some algebra to clean things up. Let's just take this first term. Let's focus on that. Well, we have a minus and an x, so that's a minus x times a 2x. So it's a minus 2x squared. Right, so I just multiplied the x and the -1 and the +2x. Oh, sorry, minus 2x squared And then we have this, the only thing left is this part in red. 1 plus x squared to the minus 2. But again, back to orientation module 0, back to the pretest. This is the same thing as making it cross, like there's an invisible fractional bar. It becomes 1 plus x squared squared. Okay, so that's this whole term here. All the stuff before the plus sign simplifies to this one fraction. Looks a little better. Plus what happens to the back, well, this whole term actually just turns out to be a fraction as well, using the exact same trick, 1 plus x squared to the positive 1, which is, we don't even have to write anything. Now I have this, a fraction plus a fraction equals 0. If we could just turn it into one fraction, we could use the trick we did like 20 minutes ago. So let's figure out, can we turn this into one fraction? Yeah, we can get a common denominator. This has a 1 plus x squared, this has a 1 plus x squared, this is another copy of that. So the common denominator would be 1 plus x squared all squared. Then we'll have some stuff that goes before the plus sign, plus some stuff that goes after the plus sign. So in front of the plus sign, we didn't change anything. We'll just have the minus 2x squared. After the plus sign, the only way to make this fraction have the denominator of 1 plus x squared all squared is I need to multiply it by 1 plus x squared. Whenever I do the numerator, I have to do the denominator. So this just becomes 1 plus x squared. So again, these are really two separate fractions. That's the first one. And then here's the second one, but I've turned them into one fraction. This little kidney bean shape over here is actually the same as that one. The whole point of turning that into one fraction was that some things will simplify in the numerator. I have 1 still there, minus an x squared. Denominator stays the same. All that equals 0. When does this fraction equal 0? When the numerator equals 0. I now have to solve the equation in red, which is a quadratic equation, but hopefully you see it's pretty easy to solve. 1 minus x squared equals 0. 1 equals x squared. X equals positive 1. X equals minus 1. Those were the two CPs that we found visually. We've now found them with calculus and algebra. Okay, I think that's probably really good. Yeah, that's great review. So we got to do local extrema, global extrema. Now it's time we get started with book 1.5. Okay, so that's book 1. Yes. Now we're ready to start this next one. First thing you notice is it's, hey, it's a whole lot thinner. I tried to only copy parts of the book that we would need. And so it's a lot less material. And the neat thing too, I think about calculus 1.5, it's very, very visual. So I think you'll see that right away in this next hour. Okay, first thing, check out page 19. All right. So we're going to be doing this as an overview of things that we're going to be able to do in Calc 1.5, which is also called integral calculus. What we just did in book 1 was called differential calculus because you were doing differentiation rules, you're taking derivatives. Here we're going to be doing integrals. That's a key word for us. They're also called antiderivatives. In a lot of ways, they're opposites of what you just did in calculus 1. There's this neat relationship. One does something, the other undoes it. So we're going to see that as we proceed. But the neat thing is we're going to be finding areas. We used to be able to, this was all you could do. The first line here was prior to calculus, you could find areas of sort of geometric shapes, right? Like circles, parallelograms, triangles, trapezoids, all sorts of geometric things. But if you were nonlinear, like over here, that's what we're going to have the power of calculus. It's going to enable us to do all sorts of crazy ones. We won't get the super crazy ones here. We'll stick here, and maybe the first couple, we'll do things like that. Another thing you can do from geometry is find like the center of a rectangle, the centroid, right? But we can also find that for nonlinear spaces over here with calculus. Next thing is how long something is. So we could use Pythagorean theorem to say the length of a line, but that was all still geometry. And calculus enables us to find the length of something that is curvy. So this might represent, I don't know, length of the Cooper River Bridge, right? So how much materials do I need to know? I need to get an estimate before I build it. I can't build it and then get out my tape measure and say how long it is, right? And we're not going to do these last couple here. So we're going to spend most of our time with the first two, finding areas. So again, hopefully you see that that's visual already. Okay, chapter 1. So we're on our chapter map here. What page is? Page 23. Those are your key terms. This is great also studying for a final to just make sure you can go back to the chapter map. Do I understand each of those terms? Do I now have like a picture in my head for each of those? As usual, this one has quite a few more activities than calculations. So you can imagine this chapter is more concepts. Chapter 2, it's vice versa. We actually have a lot more calculations. So that's the one that's more sort of programming. Like you're just programming yourself to be able to do these kinds of calculations. Okay, and as usual, a couple challenge problems and a couple tech tools, right? So you're going to learn those every time. Okay, so on page 25, first page of this chapter, at the bottom, it's always a good idea to preview the challenge problem so you can sort of put in context what it is you're trying to learn in the goal. And so there's a couple problems at the end of the chapter, and the quick summary is the first one, challenge number 1, is like, suppose you have a pizza and you want to cut it into 3 equal regions and you're only allowed to use 2 parallel slices. So those 2 parallel lines. Where do you put them so that you have equal area? So this is different than, you know, there's maybe some ways it'd be pretty complicated geometry, but it's very easy to do this with ideas from calculus. And the next one is that there's some laws, city ordinances. In fact, Folly Beach has an ordinance where you can only put a certain amount of your property has to be permeable, which means it allows water through. And so you can't have like concrete surfaces or roofs or structures only on some percentage of the property. So this is just showing an example of a property doesn't meet the rule. And so it's really a question about area. So that's our goal, our motivation to be able to do these problems. Okay, now we're going to flip the page, take a look at page 26 and 27. Here's a shape, and we want to get the area of this shape. So on page 27, we have this geometric shape. We want to get its area. And on page 26, it says you can actually approximate it with a bunch of rectangles. And so on page 26, they ask you to take a moment and match your fingers to the different rectangles. Like my pinky is probably like the third one there, right? So one pinky, and then you're wondering, could you put your fingers in here? Like how many index fingers does it take? How many pinkies? And sort of add those up. And because you have the areas of the rectangles at the bottom of the previous page, you could sum those up. So you could get an approximation using just body parts and rectangular regions. The reason we were using rectangles is because they're really easy to get the areas up, right? It's just a length times a width. And you probably do this a good bit, like if you're going into Lowe's or something, you forgot your tape measure and you're like, how long is that? Maybe you know your foot, like my foot is almost a foot, so I can just like mark it off, walk it out and estimate. Or like, you know, your height is your, what is that, Da Vinci's Vitruvian Man, right? How tall you are head to toe is the same as how, for almost everyone's matches, some people off by an inch or two, how far you are your wingspan, right? So I'm 5'8", so 5'8" here, and then 5'8" from head to toe. So you can sort of get measurements of something like, is this going to fit in my living room, this furniture, this couch, or whatever. So you use body parts a lot to get rough estimates of things. That's kind of what that page 26 and 27 are. That's an activity that you'll have for your homework that you can go through. Let's go to page 28 and 29. Okay, here's that same region drawn in like tiny little sections. So I want you to take a moment. There's 6 little copies of it. And I want you to just, in the first copy, what are some geometric shapes that you know how to get the area of easily, and try to like fit some of those in here. Like, does some of that look like maybe a triangle? Some of it look like a square? Maybe you could fit like a semicircle there. So just take a moment now and take the first one and fill it in with some shapes. Just try to like fill in that nonlinear weird area with some geometric shapes that you know. Do it for the first one, then maybe try some other shapes over here. Just take a moment to do that. Okay, now let's flip the page and see if some of your ideas are similar to what we have here on page 29. Okay, so let's see, let's look at one. This one over here. I just divided into 2 triangles. I know how to get the area of each triangle. Is length times width divided by 2, or base times height divided by 2 is probably the phrase you learned. So I could get the area of that triangle, add up the area of that triangle, and you can see from the picture, is that going to be an overestimate or an underestimate of the area? And so for each one of these, you can just visually look at it. It looks like it's an underestimate, right? The way it's drawn, that it'll give an approximation, but it'll be an underestimate of the true area. Another geometric one over here. This one, it looks like there is a rectangle, a little triangle over in the left corner, a little semicircle. Add up those 3 geometric things, get the area of each of them, add them up, and you still have an approximation, right? But it's an underestimate. It looks like there's a little less than what's actually there. And so one of the activities at the bottom of the page is circle the figure in these images here. There's what, 8, 9, 10, 11 different figures. Which one do you think gives the best approximation? So take a moment and answer that. All right, so visually, which of those 11 do you think gives the best approximation? Just looking at the picture, those trapezoid ones over here in this corner, those look pretty darn close, right? And further, another one that looks pretty close is these rectangles here, right? There's quite a few rectangles slammed in there. We made a lot of skinny little rectangles. And when you do that, when you add more shapes, often you can do a better job approximating. Trapezoids generally do a good job because the heights pretty close to the curviness. It's a decent approximation. And then squashing the width usually helps. Now, another one that looks pretty decent, I guess, maybe is that the small squares, like I could use even smaller squares, right? And get a better approximation, just maybe doubling or quadrupling the number of squares that are used should do a better job. This concept of adding more shapes or shrinking the size of the shapes, kind of analogous, that'll always help get a better approximation. And then the second question says, label each one of those 11 approximations as an overestimate or an underestimate. And again, you're just visually looking there, but like the one at the bottom, the 11th one down here, that one clearly looks like an overestimate, right? Most of the lines are outside of that region, the original blank region over here, right? So it's more than you need. Okay, so flip the page 30. Okay, we're going to learn something called Riemann sums, named after this guy, Bernhard Riemann, German mathematician. And he came up with this idea that you could fill the space just like we were doing before, but he thought it would make more sense and make the calculations easier if, rather than making them varying width, like I can get the area of a rectangle rather easily, but why don't I make them all have the same width? That way I only have to get the heights. Like the width of every rectangle is the same. And he had this idea that we could use certain rules. We're going to focus mostly on these left, right, and mid ones here in this row. There's some more advanced ones, which we already sort of saw visually. The trapezoid one from the previous page would seem to do a pretty good job. And the Simpson's rule, named after another mathematician, Thomas Simpson, English mathematician, who this one's probably the most accurate in general, but it takes the most work. So we're going to focus on these three here. Just know that these exist. You can get even better approximations. So Riemann sums are the idea of summing up rectangles. And let's just go straight to an example. So let's go to the next page. I'm going to practice this together. This is part of your homework, and we'll do a few of them here together. Okay, we want to estimate this region from this function, 0.1 x squared plus 1, which is just a parabola opening up at 1. So my y and x axis are of different scales, but that's okay. We saw that earlier today with Google. I got an advanced by hand tech tool here. Okay, so we want this region in here. We want to get the area of that. And we'd like to eventually get to like a good approximation, but we're going to start off with just a rough approximation. And the instructions for number 1 here on page 31 say they want us to do what's called a left Riemann sum with n equals 2 rectangles. So I'm going to show you how to do that. We'll do a couple of these Riemann sums, and then you'll see that they're very common sense and very visual. Okay, so the Riemann sum, we're supposed to be dividing this into rectangles. We want to use 2 rectangles, and I want to make each rectangle equal width. So from 0 to 4, I want to divide that into 2 sections. Well, that would be 0 to 2, and then 2 to 4. So I'm going to put like a partitioning wall right here. And now the next thing is I just have to, so I figured out part of the thing about a rectangle, right? A width. I just need to figure out the height of a rectangle. In order to get the height of the rectangle, I'm going to use the left rule. And that's going to be different if I use the right rule or the mid rule. And we'll go through those in a moment. Let's start with the left rule. The left rule says you go to your first rectangle, which is from 0 to 2, go to the left side. So that'd be right here at 0. Go up to the function, and that is the height of that first rectangle. Almost matches the function, but we'll see that it makes it a little clearer when I do the next one. So now I go to my second rectangle. That's from 2 to 4. go to the left side of that interval from 2 to 4, the left side's at 2, go up to the function there, go straight across, whoops, draw a horizontal line. That's the height of your rectangle. So it's just slightly bigger than the other one, just a hair taller. And so now I'm going to get the area of this shaded region. That rectangle plus that rectangle, and I'm saying that's an approximation, clearly an underestimate from the picture to the true area, which was that nonlinear thing, which is this part here. I'll just outline it in red. Right, that's what I really want. It's easy to see what I'm going to get is an underestimate. It'll probably be a pretty gross underestimate because we only use 2 rectangles. But let's go ahead and do the computation then. You want to be able to draw this picture and visualize it. That's a huge first step to doing a Riemann sum. And then you'll see that the calculation part's actually pretty straightforward. Once you've drawn the picture, you've got everything, you got the concept down. Okay, so the left approximate area is going to be 2 times something plus 2 times something. So those 2's are the widths of the rectangles. Each width is always 2 in this example. If I was using n equals 4, I'd have 4 rectangles and the width would be 1. Okay, now how do I get my heights? So let's just take the first rectangle. The first rectangle, I went to the left side when x was 0. I went up to the function there. And so that's really the point 0, f of 0. Right? Heights, if I give you an x, I go to the function and it spits out a height. What was the original function? It's right here. Y equals f of x, those are the same thing. So I want f of 0. That's 0 squared is 0 times 0.1 is 0 plus 1 is 1. So this is really the point 0, 1. That means the height of this first rectangle, this distance, is exactly 1. Okay, plus the second rectangle. I need to get the area of this second one. It has the same width. I need to figure out its height. Its height I got in a similar way, but I went to, when x was 2, which is the left side of that interval, I went up to the function. So right here, this point is actually at the point 2, f of 2. Well, to get f of 2, I go back to the original function. I plug in 2 for x. 2 squared is 4, times 0.1 is 0.4. 1 plus 0.4 is 1.4. So I'm going to sum up the area of the left rectangle plus the area of the second rectangle, and I'll have 2 plus 2.8 is 4.8. So we're saying that that area is approximately 4.8. We know that's an underestimate. We know it's probably a pretty poor estimate, and we know how to do better. So let's move on.
Wait, how'd you get the 1.4 for the second rectangle?
Okay, who's talking to me?
Lauren.
Lauren, thank you, Lauren. So this 1.4 is the height of this second rectangle. So that is this distance here. That is 1.4 is what we're saying. And how we got it, and how you get it for all these problems, is you go to the left interval, the left side of the interval, because we're using the left rule, which is 2. So there's only 2 choices there, 2 or 4. I go to 2 because I'm using the left side, go up to the function there. And so that is the point 2 f of 2. So that height, that blue line there, that distance is f of 2. How do you get a height on a graph? If you're given an x, how do you get how tall you are? You go back to the original function. This was something Shelby had us practice earlier today. So the function says, give me an x, I'll spit out a y. The x this time is 2, and it spits out. So I just did, maybe I'll break it all down for you, Lauren. Just did the computation in my head, but it's really just 0.1 times 2 squared is 4 plus 1. So that is 0.4 plus 1 is 1.4.
Okay, thank you.
Okay, other questions before we make this approximation better? Cool, okay, let's go ahead, same problem, but let's make n equal 4. So this is number 5. Actually, let's do number 6 now on that page because number 5 is already done for you. So let's do one together. That right rule with n equals 4. Yeah, n equals 4 rectangles. So let's clean up our picture. Okay, we still want this red area. That's the exact area. We won't be able to get that exactly until chapter 2. We will be able to get this exact area using antiderivatives or integrals. So it'll be next week. For now, we can get it approximately, and we know we can improve our approximation if we just like take more rectangles. So this is the first time we're gonna go from 2 to 4. We're actually gonna add more rectangles. And this region from 0 to 4 is what we want. So along the x-axis, they always have to give you a left and a right side. The left side's 0, the right side's 4. We want to divide that into 4 even sections, right? So that's pretty easy. Sometimes they give you nasty ones where you have to do fractions, but you know, no problem. This one's nice and easy, integers. Okay, so that divides x into 4 even sections. But what we have to figure out next is how tall each of these rectangles is. It's easy to see from the picture. That the widths are even, right? Well, sort of. I mean, my picture's a bit off, but it's easy to see that we did a good job with our widths. They're always 1 across, right? So it's also easy to see that we're going to be multiplying length times width for 4 different rectangles. And then we want to add all those things up, right? That'll give us an approximate area. The length times width. The width is always 1 each time. Now we just have to get the heights. We're going to do the same thing, but this time we're going to use the right rule, but it's almost exactly the same. We're going to have 4 different heights. Heights on a graph are always f values. So there's always going to be f of something. So we know, I'll make some space here. We're always going to be putting f of something. Right, each time we do that, we're adding heights. Heights are f values. What we have to do is figure out what are those x values that we're plugging into the function. So what goes in this first parentheses? That's the first rectangle. That's the one that goes from 0 to 4. Instead of using the left side over here, we're now going to use the right side over here at 1. So we're going to go to the function right there. Here's our function. F of x equals 0.1 x squared plus 1. Go and draw your height. From 1 to 2, that's our next width, our next rectangle. The second rectangle here, the right side is over here at 2. I'm going to go up to the function and draw my height. The third rectangle goes between 2 and 3. The right side of 2 and 3 would be 3. I'm going to go up to the function there, draw my height. That's my third rectangle. The fourth one, I go to the right side between 3 and 4. The right side is over here at 4. Go up to the function. That's the height of the fourth rectangle. So this page right here is a great page, page 31, to make sure you can draw every single one of these. You want to draw them left, right, and mid rule. We'll come to the mid in a moment. For different values of n, make sure you can draw the picture, show it to a neighbor, show it to a classmate, Zoom with one of your friends. This is a very efficient way to do your work and check that you've got the right ideas. Okay, now that we see the picture, that's what the right rule looks like. It's a matter of now plugging in certain values. So let's take the first rectangle. That's the one between 0 and 1. F of what do I want to evaluate? Remember, between 0 and 1, I went to the right side, which was at 1. So I really want to know what f of 1 is. The second subinterval was between 1 and 2. The right side was at 2. I went up to the function at 2. So I'm getting f of 2, 3, and 4. Now I just need to plug in those particular values, right? I see what I've done. Now I plug it in for my particular function, which is 0.1 x squared plus 1. I need to get f of 1, f of 2, f of 3, f of 4. Okay, so f of 1 is 0.1 times 1 squared plus 1. That's 1 times 0.1, which is 0.1, plus 1, which is 1.1. So maybe we'll, is it okay if I come in here and just change this? F of 1 is actually, when you evaluate it, 1.1. F of 2, when you evaluate it, you plug it into the function. The only thing that changes is right here, this becomes 2 squared. 2 squared is 4, multiply that by 0.1, you get 0.4, add 1, and you get 1.4. So when I evaluate f of 2, I get 1.4. That's how tall we are right here at this point on the graph, which is the height of the second rectangle. So f of 2, I can go ahead and fill that in right here. I have to do a couple more function evaluations. You can also ask Wolfram Alpha if you don't like doing function evaluation. You can actually type in the function, type in this and say evaluate 0.1 x squared plus 1 at x equals 3, right? And it'll do that for you. But this is a difficult one to do in our head or do by hand. F of 3, plug in 3, plug in 3. Let's see what we get. 3 squared is 9. 9 times 0.1 is 0.9 plus 1, so we get 1.9. That's what f of 3 is, so I can actually come here and put that as 1.9. One more we have to do. We need to know what f of 4 is. So I go back to my original function. I plug in 4 whenever I see an x. That's what it means to evaluate a function. It says you give me an x, I'll spit out a y, which is a height on the graph. 4 squared is 16 times 0.1 is 1.6 plus 1, so I get 2.6. That goes right here. All I have to do is do length times width, plus length times width, plus length times width, plus length times width. Add these all up. Well, the nice thing is it's a 1 times that, so it's really just 1.1 plus 1.4 plus 1.9 plus 2.6. And let's see, that's a 3 plus a 4, 7. It comes out to be exactly 7. So our approximate right area is 7. Our approximate left area with just 2 was, what did we get, 4.8 earlier? We knew 4.8 was an underestimate. We know 7 is an overestimate. So the true area lies somewhere between 4.8 and 7. If we just keep adding more rectangles, we're going to get better, right? If I asked you to do n equals 8, you could do it with the right rule. What would the width be? If I asked you to, if I change this problem and said do the right rule with n equals 8, what is the width of each rectangle? So just pause for a moment and see if you can answer that. Each one would now be a half. So I'd have to come up here and split that one, split it, split it, split it. I have 8 different sections now. I have to evaluate it at 8 different points. My picture would look a little bit more refined. My picture would look something like this. Always go to the right side and go back, right side and back. That's the picture for n equals 8 with the right rule. I'd be adding up 8 things this time. Each time I'd be adding up things that had a width of 1/2. Right, so we gotta add 4 more things, but every time the width is a half, the heights are just gonna be f of the right side. The first one was at 1/2, the second one was at 1, the next one was at 3/2, the next one was at 2, and so on, and just keep on going down, always using the right side of every interval, f of 7/2 and f of 4. Add up all those after I've done all that calculation. But the neat thing about these is you see that it's a pretty straightforward calculation, right? It's not mentally difficult to do this. It's just tedious, right? It's going to get better. The approximation's no doubt going to get better when I increase in the number of rectangles that I use. Okay, let's pause here for some questions. I think maybe Macy's got a question.
Yeah, I was just wondering super quickly, so how do you exactly know like how many rectangles you need to draw? I understand like if we're solving for the left side or the right side, and you said when you get the left side and the right side, that means that it's an approximate between the two. How would you know how many rectangles you need to draw and solve in order to get one side or the other?
Okay, great question, Macy. So these problems will always be stated in this way. They'll say, here's a function
Okay.
over a particular region. So they're going to have something like this. Get this out of the way. Suppose it's some nonlinear function like this. They have to give the equation of the function first of all. So they'd have to say, it's like ln's and e's and x squareds and whatever. They have to give you something. And then they also have to give you like a left thing that they're interested in, maybe, and they usually call this a. Maybe this is like -2 and maybe this is like 7. So they have to give you that much. And then ultimately what we want, again, where we're ultimately going in chapter 2, is we're going to get this part in red exactly. But for now, the best thing we can do is approximate it just the way you outlined, Macy, with the left or the right or the mid. They're going to ask you one of those. So they'll give you a function explicitly with a functional equation. They'll give you a left and right endpoint. They'll give you n. They'll tell you, do this with n equals 10. For this one, it might be nice if they chose, what would be a nice one, like n equals 9, right? If they chose you, they might say, do this with the midpoint rule, with n equals 9, and get an approximate area. Why did I say 9 would be easy? Because that would make the width of everything 1, right? So I'd split it here, here, 1, 2, 3, 4, 5, 6, 7. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have made that into 9 even ones, And then here's what's the part we haven't done yet, but you probably can guess at this. The midpoint rule, instead of going for every rectangle, instead of going left or right, you go to the direct midpoint or center of that. So halfway between -2 and -1 is -1.5. I'd go up to the function. That would be my height. So you want to be able to draw these. And this is what you get to practice in this chapter. There's several practice pages that are due for your homework, where you get to visualize drawing these different rectangles. And then I'm only going to ask you, so to answer Macy's question too, on the final exam, when you have to do this, or in your quizzes, I'm only going to ask you like n equals 3 or 4. I mean, these are tedious and annoying. You have to understand the idea that I could do it n equals 100. I can make a computer do n equals 100. That's what Wolfram Alpha and some of the tech tools that you're going to learn in this chapter do. It's no problem, right? It's just very straightforward. It's just annoying and tedious to do this. Easy to make little arithmetic errors too. Easy to make function evaluation errors. So I'll ask you, when I tell you, I'll give you a rule, left, right, or mid, and I will give you n, and it's usually going to be a small n, like n equals 3 or 4. But you need to understand visually the difference between left, right, and mid. You need to understand the difference when you think it's going to be overestimate or underestimate. So you need to like visualize the picture for bigger ones. And you need to, of course, understand the idea. That's pretty straightforward and obvious, that if I make n, the number of rectangles bigger, which is the same thing as making the width of each rectangle smaller, I will get a better approximation. Okay, so page 31 is a really good one to finish. You have to do it for your homework. We got you started there. And then let's go to the next page, page 32 and 33. This is also one that's due for your homework. This is another really good, if you can do this problem, I feel like you're well on your way with this chapter. If you can match these problems on the page, it'll take you some time to sit down and think about them, but you want to be able to say on the page 32, which image matches the things that you're adding up. Most of them have a width of 1, except for if you look at D on page 32, that one has a width of 1.25, so it's a little bit wider. You know, is there one of those that you think it matches? Which one of those, 1, 2, 3, 4, 5 on the left, must be D? Which one has a width of 1.25 for each of its rectangles? So if you look down there, number 5, at the bottom of the page, on page 32, number 5 is the only one that has a width of 1.25, and that must mean 5 and D match, because there's the width. And there's the different heights that are calculated. So you want to be able to look at each of these and match them to a sum, or vice versa. Maybe like looking at the algebra and matching to the picture. Next page. You want to match a picture to the type of rule. Is it a left? Is it a right? Is it a mid? How many rectangles are used? And answers at the bottom as usual. So you can check those out. That's another really good one to go over. Well, you have to do it for your homework. Okay, let's go to page 36. Look, I did a lot of calculations on there, so let's not write them on board. Let's just look at these together. This is saying, what if you use the left rule and 10 rectangles, and then use the left rule and 20 rectangles for that same problem that we were just doing on the board, that same parabola. All right, we did it with n equals 2 and n equals 4 with the left. Now if we jumped it up to 10, okay, it's tedious, but we can do it. Here's all the, it's not even, it's just arithmetic, right? It's not even algebra to do, right? We're just adding up lengths and width, 10 times, 20 times. And you look at your values, and they're getting closer, right? What are we getting closer to? When we did 20, we're at 5.98. And it's getting closer to the true value, but we don't actually know what the true value is until we go to chapter 2. But the thing we can answer at the bottom of that page, right? Fill in the box there whenever you see those check boxes. What do you think happens? Answer that question right now. as n increases, what happens to that Riemann approximation? It has to improve, right? Common sense. You're going to do page 37 as an activity. You're going to fill in those check boxes. And then you're going to do the flipbook animation. Pretty straightforward. Again, that's another one for your homework. Okay, page 39. Let's go
Can I ask a quick reminder question? Just
Yep.
like from last chapter, mainly is about CPs and APs. How do you, once you find the critical points, how do you use those to find the endpoints?
Is this Lauren?
Yes.
Yes, okay. Lauren, so Lauren wants us to review global extrema again, so this is probably a good place to, we'll pause on the Riemann sums for a moment. We've got about 20 more minutes, so this is good. We'll have time to finish what I want to finish. Okay, so global extrema, remember this was our picture. This is the picture that helps us with the study guide. We're going to compare values, x values and y values. What makes an x value, it makes it into the list if you're a CP or an EP. So this is something Lauren just mentioned. Why do those belong in the list? Because the only places global extrema can happen are at CPs, which are good places to look for local extrema, or endpoints, right? So like there's a left and right endpoint and we're only looking at that section of the graph. Those are places where you might have a global max or a global min. They only happen at those places. So we're gonna put those in a list. EPs are always given. Let's see, that problem we had earlier was like -2 and 3. And then you're gonna put any CPs that lie within that interval. For that particular problem, we found 2 CPs, -1 and +1. And then what you do with those, so that's how you make your list on the left-hand side. You only put CPs and EPs in that list. EPs are given, CPs you had to do a little work to find. Trinity gave us one that was a little bit of a doozy to find those, but we also verified them visually from the graph. So you've done some work, you found your CPs. If you're lucky, there's only 1 or 2. It's okay if a problem has no CPs, that's possible too. It'd be terrible if it had like 5 or 6. I wouldn't put that many on an exam for you, but this is a reasonable problem to have. Of these 4 points, we want to know who is the tallest and who is the smallest. That is the definition of a global extrema. Those only happen at these 4 places. So I just have to figure out of those 4, I evaluate them in the function. So I think that's your question, Lauren, is you take each one of these points and you just figure out what is f of -2. You plug it into the original function and you get a number. You figure out what is f of -1, plug it into the original function and you get a number. You just keep doing this. You're always plugging back into the function because you want to know about heights. And then you compare these 4 numbers on the right column to see who has the biggest value and then who has the smallest.
Okay, thank you.
Okay, before we go on to page 39, I just want to point out some pages we're not doing, which would be put over here. Pages 40, all the things that have to do with summation. So this would be page 40, 41, 42, 43. So pages 40 through 43, we don't do them because they are maybe more for math majors, a type of shorthand notation for this. We'll come back to this one example if we have time on page 39. I think the next thing is let's go to page 46. Okay, so this is computers and Riemann sums. And so it's just saying, hey, this stuff is pretty straightforward to think about. It's kind of maybe annoying and tedious when n gets big, but we get the idea. And so it's saying that's the kind of work that computers love to do. So you just want to answer these checkbox questions. Is this the kind of thing you think a program can be programmed to do? Yeah. Could it do it for any function if you just gave it any function f of x, as long as it's explicitly defined? Like we just did f of x equals 0.1 x squared plus 1, but it could be anything, as complicated as you want. E to the x squared minus x plus ln x over sine x. Yeah, it could do that. For any value of n, if you wanted it to do for n equals 1,000,000, you're going to have a really, really good approximation. And the computer just takes some time, but it'll do it, no problem. Could it be programmed to do the left rule? Could it be programmed to do the right rule, the mid rule, the trap, the Simpsons? You haven't learned those, but yes, any rule that you can imagine, you could program a computer to do it. And in fact, that's what computers do, like Wolfram Alpha. So that's the next tech tool page on page 47. There's some commands that you can enter into tech tools. So you can ask Wolfram Alpha, just type it in, use the right endpoint rule for the particular function with so many intervals. And then there's some really nice GeoGebra and Desmos, the bottom two. They also come with little pictures and little buttons that you can sort of slide and move around. So maybe let's take a look at, and I usually just Google the phrases that are written there. Oops. So I'm going to Google Desmos Riemann sum calculator. And a lot of instructors have put some little sort of applets together for you to use. Let's see if this one does what we want. Yeah, so here's a picture. That's a function that we don't do because we don't do sine functions, but let's just maybe change the sign to something that we do, like polynomials, x cubed. And you pick a left endpoint, say like, oh, there's -1 up to 3. Let's zoom out a bit more. Okay, from -1 to 3, those are your sort of boundaries. We don't care what happens outside of that. And we want to get a Riemann sum. This is showing it'll do the left, right, or mid. When it's set at c equals 0 in the middle, it's telling us, c equals 0 is the left-hand rule. So these pictures are drawn from the left each time. When it's below the x-axis, this particular visualization shows that it's red. These are all your little rectangles, right? So those are the heights and the widths. The widths are always, oh, sorry, I forgot. Here's n, the number of rectangles. So you can see there's a lot more white space, a lot more gap, meaning you're pretty bad underestimate when you do n equals 3. But of course, as you increase n, and this will show you, you're getting closer and closer to the function. Your approximations better be improving. And it's actually showing the answer down here. This is if you were summing up 46 different areas of rectangles, you're going to get closer to the true value. Which again, we don't know how to get that true value yet. We will. But they look like they're converging to like, I don't know, they keep on rising even though they're getting closer to 21 maybe-ish. We'll see next semester, but you can see from the next week. But you can see from the picture that those almost look exactly like the function. That makes sense visually. So those are tools that'll help you if you want to check your work. Like there's a couple, like that page 39, you have to do some of those and you can check your work with the tool. And GeoGebra is another one that's shown at the bottom there. Okay, flip the page 48 and 49. Oh, stop the share. Okay, this is just a gallery view of things that I made, little images and screenshots that I made. I think I used Desmos to do that. So there's a function at the top. It's not necessarily one we do because it's a trig function, but you get the idea. The function is this highly nonlinear function shown. That's a very light little line that is shown on. And then this is showing there's a lot of gap between the function and those rectangles when we only use n equals 4. And we're just going to increase them 8, 16, 32. And we're going to keep on going. I did all the way up to 512. And read that little caption at the bottom. That's showing you, even when you used n equals 512 and you used a computer tool, you didn't have to do this by hand, it got an approximate area of 24.88. But the exact area is shown below, 24.9499 and so on. So it didn't even give you one decimal place of accuracy. 24.8, or sorry, 24.88 versus 24.94 in a lot. So even though you used a large n, and even though visually it looks like they match, it's still an approximation. And sometimes that approximation isn't even that good. It depends on how wavy and curvy your function is, how close you expect the approximation to be. And so my point, maybe the summary of this page is that there has to be a better way besides just like doing this for n equal 1,000,000. There must be something better, and that's next week in chapter 2. Okay. The midpoint rule is shown on page 49. Same idea though, I just kept increasing n, and you see it gives a better approximation. You get 4 decimal places of accuracy if you were to use the mid rule. So if you're going to put effort in, why not use a rule that's a little more accurate? Okay, then page 50, we're not going to really do the limit, but I just want to talk about the idea here. If you're a math major, you learn how to take limits as n goes to infinity, which is a sort of like, hey, what would happen if I can make n be 1,000,000? Why can't I just make it be infinity? Wouldn't that give me the exact area? It turns out it does. And that's something like a type of hypothetical thinking. What if? You do that what if, and we're going to actually be able to do it in the limit. We're going to understand the idea of it in our head, but mathematically we're going to do it with, instead of limits, because we're not math majors, we're going to do it with something called integrals in the next chapter. So that means I can put some more pages. You don't really do page 51. It's not something we do. But you can understand page 53. This is one we can do, Cavalieri slices. And I think this is part of your homework assignment. So you're going to see this, do what the instructions say. Just take a couple minutes, draw a picture on your book, and then you answer these questions. Okay, a couple more activity pages that you have a choice of doing. And maybe just for the last few minutes, let's just talk about page 65. So you can do all sorts of neat things now that you know about areas. And so there's some facts about different states, like, what's that first one? Utah's 35% forest. Well, Utah's a pretty geometric state, so it was easier to draw, and then sketched the shaded areas or where the forest was by looking on Google Earth. And does that look like it's about 35%? How could you use ideas from Riemann's sums? Maybe not rectangles, but maybe you'd fill that with a grid of squares, and you could estimate that the area was about 35%. Nevada's less than 1% water, so another nice, pretty easy geometric shape to draw. Not much shaded region there. Again, you could estimate that using ideas from Riemann sums. Half of Wyoming is above 6,700 feet in elevation. Again, you could look at a topo map and sort of see those elevations shaded and get an approximation of that rectangular state. Then the next ones, these are actually from Google Earth. They have this time-lapse feature over time. And there's a couple ones here. The drying of the Aral Sea in Central Asia. So this is like a big body of water that in 1984 had this much water. And then it's had some drought and dried out, probably climate change. It's kind of the point of that time lapse. And so that by 2018, we have much less shaded region. You could quantify that. You can just, instead of just saying visually, it looks like this climate change has an impact on the Aral Sea, you could quantify that. You could actually say figure out how much area this is. Maybe that's 100%. And you could say how many tiny little squares you could, if you zoomed in on these images, you could put a grid over them and figure out tiny little squares on graph paper, count how many you have here versus over here. And the other one that was pretty neat was from Google Earth, the urban growth, sort of urban sprawl outside of Las Vegas, Nevada. So from 1984 up to 2018, you can look at the Google Earth images and sort of shade that region, and then you could quantify these over time. Okay, again, some challenge problems that will be, you're gonna have a choice. The last set of challenge problems, I think, are one problem from the first 2 chapters of this book. So next week, we're gonna do chapter 2. We're gonna learn how to get those areas exactly. And we will do just a sliver of chapter 3 also. That's our last little bit here. And we're gonna also say in chapter 2, not only are we gonna get exact areas, we are gonna relate derivatives, all of book 1, with something called integrals or antiderivatives in book 2, and they're inverse operations or opposites. Okay, well, that's all I had for today. So if you've got questions, please stick around and we'll do them here. But if you don't, have a good night. Enjoy your dinner, and we'll see you on Monday. Don't forget Monday's class next week.
Thank you.
Sure.
Thank you.
I have a question.
Okay.
So I'm working on challenge problem 8, and I know we didn't really go over the osculating circles. Could you go over that for a second really fast?
Yeah, I would. I'd love to see y'all add this. So is this Macy or
It's Trinity.
Trinity? Okay, cool. Okay, Trinity, so the idea, maybe I'll draw one on the board here. All right, that's the Whistler luge track. And an oscillating circle is actually an extension. It's a really cool idea. It tells you how curvy a function is at a particular point. We didn't go into curvature. There's a formula that if I give you a function, you can figure out this curvature function. And that curvature function tells you at any point on the original function. So if I could like turn this way and had an f of x, which we don't for this problem, but if I had y as a function of x, you could compute something called the k of x, which is a curvature function. And that says you give me an x and it'll spit out a k, which is how curvy you are at that x. And of course you can visually say like not so curvy here, not so curvy here, but really curvy maybe there, right? So you can estimate this. And how you estimate it visually is with something called an osculating circle. Osculating circle is an extension of tangent lines. Remember how if this is a function, I could stop at any point and draw a tangent line. Imagine I'm actually riding on a luge track, I would sail off like that. If this is the start and this is the finish, I go off like that. And here I go off like this. And here I go off like this. Right, so I could stop evenly spaced points and draw tangents. And those tangent lines, not only do they give you a direction of motion, they give you an approximation of the function there. Like the function actually is a little linelet like that, a little linelet right there, a little linelet. And those linelets are changing over time. If they change really quickly, like they don't change much over here, right? The linelets don't change much at all. And then they start to change when they hit the curve. So if you divide this in a bunch of evenly spaced points along the track, you could check out your linelets, which are linear approximations of the track. But you can get nonlinear approximations of a track with osculating circles. And that's really easy. Instead of zooming and zooming and zooming in and making your function look like a straight line, you want to zoom in and make your function look like a circle there. What is the best fit circle to your function? And so if I stopped, like say here, and tried to put in the best fit circle, well, I'd start drawing this like circle and then I just complete it. right? So then I try maybe here. I start and draw a nonlinear circle, and then it might look something like that. Maybe here it's a bit shallower, so the circle's actually really huge. When the circle is smaller and has a tighter radius, it means you're much curvier. So you can visually estimate this function that we don't know how to get by drawing these little red osculating circles by just trying to fit a circle to that section of the curve. Like right here, when it's straight, the curvature is actually called zero. The curvature is zero, which actually means that the radius of the osculating circle is 1/0, which is infinity. So this osculating circle actually is like a circle with an infinite radius, which isn't even a circle at all, right? Which means it's not curvy on this last little section of the track. But like if the well, this is probably the curviest place right here. It has the tightest little circle that approximates the function.
Okay, and when I was doing, I did like the increase and decrease on the track.
Mhm.
I turned it, so instead of it being vertical, I turned it horizontal. Is that okay?
Yeah, that's awesome. I'm excited to see what you come up with. I think you're gonna have some really good ideas, Trinity.
Yeah, I mean, I like doing the problems where like you have to find like an exact answer with math, but I also like these where you kind of get to go on your own. That's why I emailed you the other day to make sure to see what you were exactly looking for, but I like that we can kind of go in our own.
Yeah, I'm interested just to see how you think about it mathematically. And I bet you'll have ideas I didn't think of. And again, just if someone was paying, suppose someone was like, here's your job, I'm gonna pay you $50,000 just to tell me which of these tracks is the most difficult. Like, again, that people want someone that can think quantitatively and being open-ended and open-minded about something and not just being able to like apply a formula has a lot of value. So that was kind of the point of this problem. And I wanted people like you that were a little more comfortable and weren't afraid to try these. So I'm glad you're going for it.
Yeah, well, my group just kind of was like, when I was texting them back and forth, I was like, which problem do you want to do? Which problem do you want to do? And finally, last night, I was just like, we're going to do this one. And I just went with it. So now they're just kind of going with it too.
Good.
Okay, thank you.
All right, have a good night.